Welcome back to Mining of Massive Datasets. We're going to continue our lecture on MapReduce and take a look at the MapReduce computational model. So before we look at the actual MapReduce programming model, let's do a warm-up task. Now imagine you have a huge text document, maybe terabytes long, and you want to count the number of times each distinct word appears in the file. For example, you may want to find out that the word "the" appears 10 million times and the word "apple" appears 433 times, right? And some sample applications of this kind of toy example in real life are, if you have a big web server log and you want to find out how often each URL is accessed, that could be a sample application, or you might be building term statistics for a search engine. Right? So, but for now, let's just imagine that we have this one big file that's a huge text document, and our task is to count the number of times each distinct word appears in that file. So let's look at two cases. The first case is that the file itself is too large for memory, because remember we said it's a big file. But imagine that there is a few enough words in it so that all the word count pairs actually fit in memory, right? How do you solve the problem in this case? Well, it turns out that in this case, a very simple approach works. You could just build a hash table with the index by word, and the hash table for each word will store the count of the number of times that word appears. So the first time you see a word, you initialize, you add an entry to the hash table with that word and set the count to 1. And every subsequent time you see the word, you increment the count by 1. And you make a single sweep through the file. And at the end of that, you have the word count pairs for every unique word that appears in the file. So this is a simple program that all of us have written, many times in some context or the other. Now let's make it a little bit more complicated. Let's imagine that even the word count pairs don't fit in memory, right? The file's too big, it doesn't fit in memory, but there are so many distinct words in the file that you can't even hold all the distinct words in memory, right? Now, how do you go about solving the problem in this case? Well, you could try to write some kind of complicated code, but I'm lazy, so I like to use Unix file system commands to do this. And so here's how I would go about doing this. So this is a Unix command line way of doing this. Here the command birds is a little script that goes through doc.txt, which is a big text file, and it outputs the words in it, one per line. And once those words are output, I can pipe them to a sort, and the sort sorts the output of that. And once you sort it, all occurrences of the same word come together. And once you do that, you can pipe it to another little handy utility called unique. And one of the nifty features of unique is the -c option. And when you do unique -c, what unique -c does is it takes a run of the occurrences of the same word, and it just counts the occurrences of the same word. So the output of this is going to be word count pairs, right? So I'm sure many of you have done something like this. And if you've done something like this, you've actually done something that's like MapReduce, right? So this case actually captures the essence of MapReduce. And the nice thing about this kind of implementation is that it's very naturally parallelizable, as we'll see in a moment. So let's look at an overview of MapReduce using this example, right? So the first step that we did was we took the document, which was our input, and we wrote a script called words that output one word to a line, right? And this is what's called the map function in MapReduce. The map function scans the input file record at a time, and for each record, it pulls out something that you care about. In this case, it was words. And the thing that you output for each record, you can output one or multiple things for each records. And the things that you output are called keys. Okay? The second step is to group by key. And this is what the sort step was doing. It grouped all the keys with the same value together, right? And the third step is the unique minus C step. That's the reduce piece of MapReduce. And once the reducer looks at all the keys with the same value, and then it runs some kind of function. In this case, it counted the number of times each key occurred, but it could be something much more complicated. And once it does that kind of analysis, it has an answer which it then writes out. Okay, so this is MapReduce in a nutshell. Now, the outline of this computation actually stays the same for any MapReduce computation. What changes is that you change the map function and the reduce function to fit the problem that you're actually solving. Right? In this case, for the bird count, the map and the reduce function were quite simple. In some other problems, the map and the reduce functions might be more complicated. Here's another way of looking at it. You start with a bunch of key value pairs, so here's K, V. K stands for key and V stands for value. The map step takes the key value pairs and maps them to intermediate key value pairs. Okay. So for example, you run the map on the first key value pair here, KB, and it actually outputs two intermediate key value pairs. And the intermediate key value pairs did not have the same key as the input key value pair. They could be different keys, and there could be multiple of them. The values, although they look the same here, they both say V, the values could be different as well. Okay. And notice in this case, we started with one input key value pair, and the map function produced multiple intermediate key value pairs. So there could be 0, 1, or multiple intermediate key value pairs for each input key value pair. Now let's do it again for the second key value pair. Let's apply the map function, and it turns out that in this case we have only one key value pair in the intermediate key value pair in the output. And so on. So we run through the entire input file, apply the map function to each input record, and create intermediate key value pairs. Now the next step is to take these intermediate key value pairs and group them by key. Right? So all the intermediate key value pairs that have the same key are grouped together. So it turns out that there are 3 values with the first key, 2 values with the second key, and so on, and they all get grouped together. And this is done by sorting by key and then grouping together the value with the values with the same key. And these are all different values, although I use the same symbol V here. Now, once you have these key value groups, then the final step is the reducer. The reducer takes a look at a single key value group as input, and it produces an output that has the same key, but it combines the values, all the values for a given key into a single value. For example, it could add up all the values. Or it could multiply them, or it could take their average, or it could do something more complicated with all the values for a given key. And finally, it outputs a single value for the key. Right, and so when you apply the reducer to the second key value group, you get another output, and so on. And once you've applied the reducer to all the intermediate key value groups, you get the final output. So more formally, the input to MapReduce is a set of key value pairs, and the programmer has to specify 2 methods. The first method is a map method, and the map method takes an input key value pair and produces a set of intermediate key value pairs, 0 or more intermediate key value pairs. and there is one map call for every input key value pairs. The reduce function takes an intermediate key value group. The intermediate key value group consists of a key and a set of values for that key. And the output can consist of 1, 0, 1, or multiple key value pairs. Once again, the key is the same as the input key, but the value is obtained by combining the input values in some manner. For example, you might add up the input values, and that could be the output v double prime here. So let's look at the word count example and run that through the MapReduce process again. Here's our big document, and I hope you can see the text of this document, but it doesn't matter. You can see that there are words in there, so we're going to take this big document and we're going to take the map function that's provided by the programmer. The map function reads the input and produces a set of key value pairs. And the key value pairs in this case are going to be the key, each word is going to be a key, and the value is going to be the number 1, right? So for example, the word the and 1, crew and 1, and so on, and the word the appears again, and so there's another the 1 here, and so on. So these are the intermediate key value pairs that are produced by the map function. Now the next step is the group by key step, which collects together all pairs with the same key. So you can see that there are two tuples, two intermediate tuples with the key crew, and those are collected together here. There's one with with the word space. There are 3 with the word the, and so on. So, and they're all sorted and collected together in this in this place here. And the final step is the reduce step. The reduce step collects together all the values. So the reduce step adds together the 2 ones from crew. And figures out that there are two occurrences of the word crew. Space as 1. There are 3 tuples with 1 for the. They're all added together, and the output is 3, and so on. Right. So this is a schematic of the MapReduce word counting example. Now, of course, this whole example doesn't run on a single node. The data is actually distributed across multiple input nodes. So let's take that into account and see. Here's the data. The data is actually divided here into multiple nodes. Let's say the first portion of the file is chunk 1, and it's on one node. The second portion of the file here is chunk 2, which is on a different node. The third portion is chunk 3, and the fourth portion is chunk 4, and each of these is on a different node. Now, the map tasks are going to be run on each of these 4 different nodes. There's going to be a map task that's run on chunk 1 that just looks at this portion, the first portion of the file. A map task that's run on chunk 2 that just looks at the second portion of the file, and so on. And the outputs of those map tasks will therefore be produced on 4 different nodes, like so. So here's the first chunk of map output, the second chunk of map output, which is on another node, the third chunk of map output, which is on a third node, and the fourth chunk of map output, which is on yet another node. Right? Now the output of the map functions are therefore spread across multiple nodes. And what the system then does is that it copies the map outputs onto a single node, and then so you can see the data from all these 4 nodes flowing into this single node here. And once the data has flowed to the single node, it can then sort it by key and then do the final reduce step. Okay. Now, it's a little bit trickier than this, unfortunately, because you may not want to use to move all the data from all the map nodes. There may be a lot of it into a single reduce node and sort it there. That might be a lot of sorting. So in practice, you use multiple reduce nodes as well. And when when you run a MapReduce job, you can say, you can tell the system to use a certain number of reduce nodes. Let's say you tell the system, in this case, to use 3 reduce nodes. So if you use 3 reduce nodes, then the MapReduce system is smart enough to split the output of the map into three reduce nodes, and it makes sure that for any given key, in this case all instances of regardless of which map node they start out from, always end up at the same reduce node. Right? So all instances of whether it started from map node 1 or map node 2, ended up at reduce node 2 in this case. And all instances of the word crew, regardless of whether they started from map node 1 or map node 4, ended up at reduce node 1. And this is done by using a hash function. Right? So the system uses a hash function that hashes each map key and determines a single reduce node to ship that tuple to. Right? And this ensures that all tuples with the same key end up at the same reduce node. And once tuples end up at a reduce node, they get sorted as before on each reduce node, and the result is created now on multiple reduce nodes. So, for example, the result for crew is now on reduce node 1. The result for is now on reduce node 2, and the results for shuttle and recently are on reduce node 3. So the final result is actually now spread across 3 nodes in the system. Which is perfectly fine because you're dealing with a distributed file system, which knows that your file is now spread across 3 nodes in the system. So you can still access it as a single file in your client, and the system knows to access the data from those three independent nodes. One final point before we move on from the slide is that all this magic, the MapReduce magic, is implemented to use as far as possible only sequential scans of disk as opposed to random accesses. If you think a little bit carefully about all the steps that I mentioned, about how the map function is applied on the input files record by record, how the sorting is done, and so on, a moment's thought will make it apparent that you can actually implement all of this by using only sequential reads of disk and never using random accesses of disk. Now this is super important because sequential reads are much more efficient than random accesses to disk. If you remember from your basics of database systems, it takes much longer to do random seeks than to do a single sequential access of a file, and that's why the whole MapReduce system is built around doing only sequential reads of files and never random accesses. So here's the actual pseudocode for the word count using MapReduce. Remember, the programmer is required to provide 2 functions, a map function and a reduce function. And this is the map function right here. The map function takes a key and a value, and its output has to be a set of intermediate key value pairs. Now the key in this case is a document name, and the value is the text of the document. The map function itself is very simple in this case. It scans the input document, and for each word in the input document, value, remember, is the input document. For each word in the input document, it emits that word and the number 1. So it's a tuple whose key is the word and whose value is the number 1. And here's the reduce function. The reduce function, remember, takes a key and a set of values. The set of values all correspond to the same key, and in this case, it just iterates through all the values and sums them up, and the output has the same key, and the value is the sum. We look at a very simple example of word count using MapReduce. Now let's look at a couple more examples. Here's another example. Suppose we have a large web corpus that we've crawled, and for each, and we have a metadata file for our crawl. And each record in the metadata file looks like this. It has a URL, the size of the file, the date it was crawled, and various other pieces of data. Now the problem is for each host, we want to find the total number of bytes. Not for each URL, but for each host. Remember, there could be multiple, many URLs with the same host name in the crawl, and we want to find the number of bytes associated with each host, not with each URL. Right? Clearly, the number of bytes associated with the host is just the sum of the number of bytes associated with all the URLs for the host, and this is very easy to implement in MapReduce. The mapper, in this case, the map function, just looks at each record, and it looks at the URL of the record and outputs the host name of the URL and the size. Right? The reduce function just sums the sizes for each host, right? And at the end of it, you will have the size of each host. Here's another example. Let's say you're building a language model. You have a large collection of documents, and you want to build a language model, this language model, for some reason, requires the count of every 5-word sequence. Every unique 5-word sequence occurs in a large corpus of document. Earlier, we looked at counting each unique word. This example asks for each 5-word sequence. It turns out that the solution is not very different. Just the map function differs. The map function extracts, goes through each document and outputs every 5-word sequence in the document. The reduce function just combines those counts and adds them up, and you have the output. So I hope these simple examples illustrate how MapReduce works. In the next section, we're going to understand how the underlying system actually implements some of the magic that makes MapReduce work.